Hello everyone, let us continue our discussion about the quadratic forms. Now, let us talk about classification of quadratic forms. So, you may wonder why do we need to classify the quadratic forms, or what can be a starting point for the purpose regarding classification of quadratic forms. So, let us take this example. Say q1 is x1 square plus x2 square and q2 is x1 square plus x2 square minus twice x1 x2. So there is a difference of only one term between Q1 and Q2. Now let us assume that x1, x2 both are real numbers. So Q1 becomes 0 if and only if x1 and x2 both are equal to 0. It means that the quadratic form vanishes when both x1 x2 are zeros. Whereas if you look at the second quadratic form, the second quadratic forms become 0 even when x1 x2 are non-zeros. For example, if you take x1 equal to 1, x2 equal to 1, then you will get x1 square 1, x2 square 1, and twice x1, x2 will be again 2. So 1 plus 1, 2 minus 2, 0. So even when x1, x2 both are non-zeros, q2 is becoming 0. So it's of interest to notice that different quadratic forms become 0 under different conditions. So Q1 is not becoming 0 unless x1, x2 both are equal to zeros, whereas Q2 is becoming 0 even when neither of them is equal to 0. So let us try to use this as a starting point and try to classify quadratic forms into different categories. So here it is. So a real quadratic form x prime ax is said to be, now this here comes the first category, non-negative definite if the quadratic form is always greater than or equal to 0 for every x in n-dimensional Euclidean space, that is Rn. So let us try to understand this. What do we mean by non-negative definite? Means the quadratic form is definitely non-negative. So no matter what type of value x has, x prime x is always going to be non-negative. Now, what does it mean? Note that x prime ax will be 0 when x is equal to 0. And that is true for all quadratic forms. Whenever you choose x itself is a null vector, whenever you choose x itself as a null vector, x prime x is always going to be 0. So what are the other possibilities when x prime x is equal to 0 but x itself is not equal to 0, or x prime x is greater than 0 even when x is not equal to 0, etc. So this is what all we are thinking about. So what do we mean by non-negative definite? Let us come back to this. So here x prime x is greater than or equal to 0 for every x in Rn. So when x is 0, x prime x will be 0. But even when x is non-zero vector, even then for all such values of x, x prime x is going to be either 0 or it will be greater than 0. But it will never be negative. And that's why we call it as non-negative definite. Means the quadratic form is definitely non-negative. Now let us move to the positive definite. So positive definite, so a given quadratic form is positive definite if x prime ax is greater than 0 for every x not equal to 0. Because when x is equal to 0, every quadratic form is going to be 0. So let us consider a stricter condition. Now here, the quadratic form is strictly greater than 0. So quadratic form is a positive real number for every vector x which is not equal to 0. So even if entire x lies in the negative domain, say each x1, x2, xn, each value in in the vector x, that is x1, x2, xn, even if you take all of them to be non-negative, to be negative, still x prime x is going to be greater than 0. So this means that the quadratic form will be positive definite always, or or alternatively we can say that the quadratic form is positive definitely. and so we are calling it as a positively finite quadratic form. Now what is the difference between non-negatively finite and positively finite? So when you say that a quadratic form is positively finite, it means it is always greater than 0, no matter what kind of value of x you have, obviously other than 0. Now in case of non-negatively finite, the quadratic form is always greater than or equal to 0 for every x in n-dimensional Euclidean space. So you may say why we are not including the condition x not equal to 0 here, because here x prime x is allowed to be equal to 0 or it can be greater than 0, and so the condition x not equal to 0 need not be mentioned here. Now let us move to the next category of quadratic form, that is non-positive definite quadratic form, abbreviated as NPD. So this non-negative definite is abbreviated as NND, positive definite is abbreviated as PD, and non-positive definite is abbreviated as NPD. So what does it mean? So now from the first two definitions you must have got the idea. Non-positive means it never becomes positive. Means either it is equal to 0 or it is less than 0, and this happens for any vector in n-dimensional Euclidean space. Now let us move to the next category, that is negative definite. So this is exactly opposite of positive definite. So here quadratic form is always negative for every value of x in the n-dimensional Euclidean space which is not equal to 0. And lastly, the quadratic form is indefinite if it is neither non-negative definite or non-positive definite. Means if the quadratic form takes values, negative values for some values of x, and if it becomes positive for some values of x, and then it becomes 0 for some other values of x, then such a quadratic form cannot be classified. So such a quadratic form which is neither non-negative definite nor non-positive definite is called as indefinite. So these are not, this is not the end. There are two more categories. So here they are. So quadratic form is positive semi-definite. Now this is slightly different from non-negative definite. So how does it differ? How does it differ? So in case of, okay, let us first consider positive definite. Then we will talk about its comparison with non-negative definite. So a quadratic form is greater than or equal to 0 for every value of x, but there exists a non-zero value of x called as x naught, for which the quadratic form vanishes. So positive semi-definite means that we can come up with a non-zero vector x at which the quadratic form is itself becoming 0. Then such a quadratic form is positive definite. So when you say that a quadratic form is non-negative definite, then it's not necessary that we will always have x for which this will happen. So let us consider a similar category which is negative semi-definite. So herein the quadratic form is always less than or equal to 0, and moreover we can find a non-zero vector x in n-dimensional Euclidean space which we are denoting by x naught, such that the quadratic form becomes 0 at this point. So x naught transpose A x naught is 0. Now let us try to understand the difference between the categories. So here, suppose a quadratic form is positive definite. Does it fulfill this condition? Suppose a quadratic form is negative definite. Can we call it to be negative semi-definite also? So these are the questions. Every non-zero quadratic form belongs to exactly one of the categories. Which one? It can be either positive definite or positive semi-definite or negative definite or negative semi-definite. So these four, positive definite or positive semi-definite or negative definite or negative semi-definite. So you may have a question now, why do we need all of this? Why do we need quadratic forms and why do we need to classify them? So we'll try to answer these questions also, but the remark here is more important. So let us This remark is going to help us to understand the relation between different categories of quadratic forms. So when you say a positive definite quadratic form, it automatically fulfills the condition of non-negative definite also. So let us see how. So when you say a quadratic form is positive definite, it means x prime x is greater than 0 for every x not equal to 0. Now, NND, the non-negative definite means x prime x is greater than or equal to 0 for every x in Rn. So automatically here, the quadratic form is either greater than 0 or equal to 0. So when you say non-negative definite, the quadratic form is either greater than 0 or equal to 0 for every x in Rn. So this condition is being fulfilled when you have this. So when you take, suppose a given quadratic form is positive definite, then what do we have? We have x prime x greater than 0 for every x not equal to 0 and x prime x equal to 0 for x equal to 0. Means x prime x is either greater than 0 or equal to 0 if we consider all values of x in Rn, which is nothing but the condition of non-negative definite. Hence, we can say that every quadratic form which is positive definite is also non-negative definite. In the similar manner, we can say that every non-negative, every negative definite quadratic form is also negative, sorry, every negative definite quadratic form is also non-positive definite. Now let us see this, the third, that if a quadratic form is non-positive definite, then it is possible if and only if x prime minus ax is non-negative definite. Similarly, x prime ax is negative definite if and only if x prime minus ax is positive definite. So these are coming by applying the definitions of positive definite, negative definite, non-positive definite and non-negative definite. Then the next remark is a non-negative definite quadratic form which is not positive definite. It's said to be positive semi-definite. Now let us try to understand this. A non-negative definite quadratic form means, here comes the definition. X prime x is greater than or equal to 0 for every x in Rn. But it is not positive definite. The quadratic form is not a non-negative definite form which is not positive definite. So we have a quadratic form which is non-negative definite but it is not positive definite. Means I cannot, means if I take a non-zero vector x, then I may end up getting x prime x equal to 0. And therefore, it means that I can find a vector x naught such that x naught itself is not equal to 0, but x prime x naught transpose a x naught is becoming 0. Then only we can have a non-negative definite quadratic form which is not positive definite. So this satisfies the definition of positive semi-definite and hence we have this remark that a non-negative definite quadratic form which is not positive definite is said to be positive semi-definite. In the same manner, a non-positive definite quadratic form which is not negative definite is said to be negative semi-definite. So I hope this helps you to understand the classification of quadratic forms. Now let us continue this further, a minor result, and then in the next lecture we shall talk about Chomsky factorization. So let A be a positive definite matrix of order m. Then if we have all the diagonal elements of A greater than 0, and if A is only positive semi-definite, so if we have a positive definite matrix, then all the diagonal elements of A are greater than 0. And if we have a positive semi-definite matrix, then all the elements, diagonal elements of A are either greater than 0 or equal to 0. So what do we mean by positive definite matrix? So when we have a quadratic form x prime x positive definite, then the matrix A is said to be positive definite. In the same way, all other matrices involved in the quadratic form are called as per the category of the quadratic form.